In programming, you'll find that one of the most common things that you'll end up doing is sorting things. And so let's learn how to do that. Here I've created a list of elements, and we kind of want to put them in order. Now, again, from a human perspective, this is maybe a little bit easier because we can kind of see the whole list at one at a time. So, you might think, oh, okay, I'll put the 2 next, and kind of move that there, and move it into place. And so what you might do if a list was exceptionally scrambled here, let's do a different example where the 1 isn't in the correct place, and I have maybe something like this where it's 2, and then 1, and then 4, and then 3. What you might think to do, if you're sorting it, is kind of move things around in the order that they should go in. So, if I was looking at this from a human perspective, I might go, okay, well, the 1 goes first, I'll move that here to the first position, and then I'll put the 2 here, and then I'll put the 3 here, and the 4 here. And so this one's pretty trivial, right, because the numbers are small. And if we were to do another example where we had numbers that are a little more like spread out, then I might have like 6 and 20 and then 3 and then 34. And as this list grows bigger, you might think, well, okay, one way I could do this is I could pick whatever's the smallest and put it at the beginning, and then find the next smallest and put it at the beginning, and keep doing that. Or vice versa, find the biggest and put it at the end, and continue to do that. And so I think this is kind of an intuitive way to do it if you were asked to sort a list of big numbers, or a big list of numbers rather, and you had to do it manually. And so the first algorithm I'm going to talk about is going to do exactly just that. It's going to use that same intuition. And that algorithm that we're going to talk about is called selection sort. So we're going to talk about 2 algorithms. The next one is the one that we'll want to use a little bit more than this one, but selection sort I think is a good start because it's kind of intuitive. So what selection sort does is it identifies either the biggest number, so the maximum, or the smallest number out of what we haven't sorted yet. Here, let's do an example where we just have 2, 3, 1, and 4. So I'll do the max version of selection sort. Let's do that one. And so what I'm going to do is I'm going to try and figure out what is the biggest number in this one, and then once I find that biggest number, I'm going to swap it to the end. For the sake of the example, let me actually swap these around a little bit. Let me put the 4 here and 3 here. The reason I do that is just so that 4 isn't already in the correct space. So if I look at this, what I might do is we said we can only really look at 1 or maybe 2 things at the same time when we're dealing with going through an array. And so what I need to do is keep track of what is the biggest number, and then look through the rest of the numbers and see, well, is this one bigger? And if so, I need to update it. So what I'll do here is I'm going to keep something that just keeps track of the biggest number. And if we start at the beginning, then we might as well always make that number 2 by default, whatever the beginning of the array is. So here it's going to be 2. And what we'll do is we'll just look through the array and see, is there anything bigger? So if we look at the next position, we see that there's a 4, which is in fact bigger than 2. And so now we'll say, okay, that's the biggest one in the array. What I think we should also keep track of is a pointer, not in the traditional sense, but just a where is this value. So I'm going to call this index, and the index of 4 is 1. So first we started with 2, which is 0, so I would say always start with the 1 at index 0, and then whenever you find a new one, just update it to where it is. So we find that the new biggest one is 4. If I look at the next place, it's 1, which is not bigger than 4. So my biggest is still going to be 4. I finally get to the last one, and I say, okay, well, is this one sorted? And 3 is not bigger than 4, so 4 is my biggest if I look at all 4 of these. And so on the next step, what we're going to do is we're going to swap the 4 and the 3. So what we're going to do is just move the 4 to the end of the array and then swap it with 3. That way we kind of have a fast way to move the 4 to the end without having to rearrange everything in some kind of crazy way. So here I'm going to put the 3 second, and then the 1 comes there, and then now the 4 is good. And so what's good about this is that we now know for sure that the 4 is in the correct place because it was the biggest one, right? So as far as our next check is going to go, we're going to do exactly the same thing, except we can stop right before the 4. So the idea here is that with the unsorted list, whatever that may be, we're always going to look for the biggest element when going through. So here, if I was to go through again, so again, we'll just say the index of the biggest one will always set to 0, which is going to be the number. So here, I'll just put something that represents the number. It's going to be 2. So we look at the first element, we say, okay, well, that's the biggest one so far. 2 is the biggest one if I just look only at the first thing. If I look at the first 2 things, the next number is 3, which is bigger than 2. So that is my biggest one, and which means that my biggest number is at index 1. I look at the next number, which is a 1, and I say, well, okay, that's not bigger than 3, so I don't need to update my index or the number that is my maximum. And so 3 ends up being our biggest number when we look at just the 3 things that haven't been sorted, so that everything that's not 4. And so again, whenever we finish going through the list, all we're going to do is we're going to swap these 2 things. Right? So as far as our next look through the array, we're going to have 2 still here, the 3 and, oh, I put the arrows in a bad place. I need to swap it with the end of the unsorted array, which is 1. So here I'm going to move the 1 here, move the 3 here, so now the 3 is for sure sorted, right? We're guaranteed that because it was the biggest out of what was remaining. And the 4 we already know was sorted because we did that one earlier. So you may notice that every single time, once we find the max of the unsorted array, the part in black here, then we add to the end of the sorted array, which is kind of like the end of what would happen if the whole thing was sorted. Right, and so this last one, what we would do, right, is we would again start where is the biggest number, and we would guess 0 to begin with. We would always want to say, well, we might as well try to do the first one. And in this case, the number is 2, and we would look at the number to the right of 2 and say, 1, well, no, that's not bigger than 2, so 2 is my biggest number, and it's located at index 0, and again, we just swap it with whatever the end of the unsorted list is. And so here we finally get that 2, 3, and 4 are sorted, and we can kind of stop one step early. So I could go through again and say, well, is 1 bigger than any of the numbers that are currently unsorted? And, well, it has to be because it's the only one there. So our list is now sorted. We've got it in the order 1, 2, 3, 4. So to summarize, the idea behind selection sort is look through your array, basically do the linear search that we described earlier. Start at the beginning, go to the end, at least to where is unsorted, and then if you find something that is the biggest, you simply move it to the end, because if it's the unsorted part and you find the biggest, then it belongs at the end in the sorted version of the list. So let's go ahead and try to program this really quick. Okay, so I finally finished writing the code. I've implemented a bunch of stuff just to help us, but really what we're going to focus on is doing these 2 sorts here. So we're going to start with selection sort, just to take a quick look at the functions I've written. Basically, I just randomly generate an array. So I have a seeding of the random here. I create the array, and then I am going to make a random array. So I wrote a function that just generates a bunch of random numbers and puts them into an array, and then I'm going to show the array before sorting it, and then we're going to sort it and see what it looks like. So let's go ahead and try to print selection sort here. So we said we're going to need to go ahead and try to find the max every single time. So first things first, let's worry about that. So I'm going to say for int, I'm actually going to use the letter j just because I have some foresight. J is less than length. So we're going to fix this later, but I'm going to say j is less than length. So basically go to the end and see if we can find the max. Now what I should probably do is I should probably create a variable that holds the max. Ideally you would only keep an index here, but I'm going to keep both of these, a max and an index, just for the sake of our example. And so the max is going to find the max from what we've seen so far, and then the index is just going to keep track of where it is. So we know that at the beginning that the max is going to be whatever the first element is, so it's going to be the first element in the array, and then the index is just going to be 0. So notice that the zeros match up. We're getting the first element, which is in the 0th position, and then the index is that position, which is just 0 here. So we're saying, well, by default, we're just going to say that the max is 0. And so what we need to do is we need to go through the array, which is what this is doing, right? It's going from 0 to length, And if we find a number that's bigger, then we're going to keep track of that one. So first things first, let's go ahead and say if the current number, which is going to be r sub j. One other thing I guess I can do is I can set this equal to 1. We don't need to check the 0th element twice because we already stored it here. So well, let's just say j is equal to 1. If this element, so r sub j is the current element, if we move that arrow along in the array, it's the current one we're looking at. If that one is bigger than our max, then we need to update our max. Then our max is this new number because it's bigger, and you put an equal. And we also need to update our index, which is j, since j is the one that's going through. And that would about do it. So this code here finds the max of an array. And so that's great. That was part of it. But so far with what we have, this is only going to find the max one time. So this is going to find the one max, and then we don't even move it, so it really just finds the max, and that's it. So the other part we said we needed to do was we needed to go through and do this for every single element. So consider what we're doing is we're finding the max every single time. We're moving it into the position that it needs to go into in our sorted array. So what amount of times we need to do this is going to be the length, minus 1 technically, but we need to do this until the entire array is sorted, right? So there's going to be length many things that we're going to need to sort because there are length many things in the array. And so on the outer loop here, I'm going to create another loop. I'm going to use I, so this is why I use j for the inside, and I am going to go from I less than length, and then I plus plus. Okay. And so now what we're doing is we are finding the max, so let me comment this, of the unsorted array. And so we already said this code just finds the max correctly, so this will find the max length many times. And if we find the max every single time, we know from what we are looking at visually earlier that this will generate a sorted list. Now there is something that I need to do, which is the fact that we said we don't want to kind of overstep our boundaries, right? And with this example here, I didn't want to, when I was looking for the max between 2, 3, and 1, I didn't want to overstep and look at 4 again, because that was already a max I've looked at. And so in order to do that, we know that the length is basically the end of our array. And if I've sorted a number of things, in this case, I represents how many things we've sorted because it's how many maxes we've found, then I can subtract I from the length, and it will stop right before the end of it, right? So on the first loop, it will be length minus 0, so it'll just go to the end like normal. And then on the next loop, it'll do length minus 1, which is going to be, you know, with the max at the end, so it won't start up to that point, and it will keep kind of shrinking, right? I is going to get bigger because it's increasing here, so the stopping point is going to decrease by 1 every single time. And that 1 comes from the fact that we have one more sorted element every single time. We can comment this a little bit more, so just so it's clear. So if the current number is bigger than our max, it is the new max, right? And so we'll keep track of that. And then we said make the first number the max by default. And just to reiterate, you can do a minimum version of this too, where you kind of traverse from the right to left, or find the minimum and then just swap it with the beginning point. Anyways, so that about does it, although we are missing one final thing. And so we locate the max every single time, but we're not actually doing anything with it. We're just finding it, and then, you know, that's great. We found the max. That's about it. So we need to actually move this to the end, right? Is where we said the max belongs. If we're sorting things in this non-descending order, where things generally get bigger or stay the same as you go from left to right, then we're going to need to move the biggest one to the end where it belongs. So if we're doing kind of least to greatest almost, we need to move the greatest to the end, and everything else can stay where it is. So let's do the swap. So swap the max to the end, and you'll find whenever you do any sort of sorting that you're going to need to do this swap. All right, so what I'm going to do here is I'm going to create one more variable called temp, and we're going to need that. So first I'm going to write this the naive way, and then we'll explain why it's wrong. So what I'm going to do here is, well, we know that we need to swap it to the end, and we said earlier that the end of the array is at length minus I, and then minus 1 technically, because we need to offset one more, right, because we start counting at 0. So this is the end of the array, and then I need to swap that with the place that we found the max at. So that would be my array sub index. Right? And so, okay, well, we moved and copied the max to the end of the array, and so we need to swap it, so we might as well just do the other way around. Now, there's an issue with this. Right? So I'm just going to copy and paste this. And so if you think about it for a little bit here, you might realize the issue is that we're doing assignment, right, where the left-hand side gets assigned to the right-hand side, so it gets equal to it and it overwrites it. So if I find the max and copy it to the end is now the max, and I lost the old one. Whatever was at the end of the array, I lost. Now let's take a quick look at this visually with the open board here. So I'll grab this, and so if I was to say, let's just say, swap the 4 and the 3 here, right? So let's make a copy of this array, just look at. So we said, this is what we had at the end of our loop. We had a 2, we had a 4, we had a 1, and we had a 3, and we were saying, okay, I'm going to swap this one and this one. And so this was position 1, and this was position 3. And in the context of our program that we just wrote, this would be the array sub index because it was where the max was located, and this one would be the array sub length minus I minus 1, and I in this case would be 0 because we had sorted 0 things so far. Right, so if I did that, where I said R, for the sake of making my writing short, I'm just going to say end, which is 3, is equal to the R sub index where the max is. Then consider what this does is it's going to copy the 4 over to here, right? So this has gone away, now that's a 4. Now I have 2 4s, and the 3 is gone, I've lost it, I overwrote it, and I can never find it again. So in order to avoid this, what we have to do first, let me get that 3 back so we can use it, is I'm going to need a temporary variable. So this is why I created one in the code. I'm going to need to store a copy of one of the two, either the 4 or the 3. I can choose either one. I'm just going to say, let's just choose the 3, kind of arbitrarily. And so this keeps a copy of 3. So let's just say, okay, well, let's keep the 3 here. And then now when I do the overwriting, so make sure that the one you copied is the one that you're overwriting first. The order does matter here. These two need to be the same. Is going to be my R sub index. This will now copy the 4 over to here, where it belongs. So this is a 4 now. And I have a copy of the 3, so I didn't totally just lose it, which is good, because I don't want to lose it. And so we'll say now the R sub index is equal to the temp. And this will just grab this copy up here that we kept, and it will use it to overwrite this one, 3. And there we go. So now the 3 and the 4 are successfully swapped as they should be. Let's go ahead and implement this really quick. Should just be 3 lines of code. Very important to remember this. It is going to be super common. You'll write it all the time because sorting is very common and swapping is generally something you're going to have to do when you do it. So I created a temp variable and I'm going to set it equal to the end, which was this calculation here. I should probably, for the sake of readability, let me create another variable called end index. I'll camel case it, end index, and I'm going to set end index to this thing. So end index equals this, just so it's obvious for everyone. Find the index of the end of the unsorted array. Way it's more clear for everybody to be able to read it. And I realize I could do this better, right? I could increment or decrement a number here and just keep track of that, so I could cut down on computation. But this is fine. That's all right. No big deal. So this should swap now. And let's just see this in action really quick. Now that we're done with selection sort, let's go ahead and compile, and we should see that it works. So we do not. Okay, so right after I explained what you shouldn't do, I forgot to fix the code that I was using to explain the fact that it's wrong. So this should be temp, right? We said that we need to copy the temp over to the variable. So now if we run it, hopefully it should work. We'll see here if we run it that it generates a random array, So we have all these numbers, 18, 11, negative 7, negative 15, negative 8, all that. And then after sorting with selection sort, it seems like they're all in the right order, right? Negative 8 smallest, and then they go up over time until we hit 36. And then here we have a second example that we'll get into in a second, and we'll sort that as well. But there we go. Selection sort seems to work, and it's pretty cool. It works, and it puts things in order. So now we might be able to keep track of things and have an easier time finding things if we were to look them up. Let's end things off by talking about a second algorithm that can be optimized a little bit better than selection sort. Let's take a look at bubble sort now. Bubble sort is a little bit better than selection sort, and it can be optimized a bit better, so I recommend using this one over selection sort. The idea behind bubble sort is very similar to selection sort in that we are always going to move the max to the end of the array. The difference here is that we're going to do it in a different way. So rather than find the max and just move that to the end, we're going to try to bubble it, hence the name bubble sort, to the top. And then we'll also kind of move things that are out of place closer to where they belong as well, and this may allow us to optimize this in some way. So rather than looking at one single element at a time, which is what we did with selection sort, we checked each one and said, is this the max or not, and just kind of went through the array. What we're going to do is we're just going to check which one is the biggest between any two adjacent numbers. And so what we're going to kind of do, rather than just point at one here like we had previously, where we just pointed this one and then that one and so on, is we're going to kind of keep a window. So I'm going to look at these two first. Maybe red is a little bit easier to see. Let's do that. We're going to look at these two here, 3 and 4, and then after that we're going to look at these next two, and then the next two, 2 and 5, and then 5 and 1. So we're going to look at every adjacent pair that we can possibly do. And so if I look at the first two here, I'm going to see 3 and 4, and what I want to check is, are these in order? And so if I look at just 3 and 4 individually, those two by themselves are sorted, because 3 and 4, well, 4 comes after 3, so that's okay. But if I look at the next part here, the 4 and the 2, these are out of order. And so in this case, I'm going to swap them. So I'm going to make this a 2 and this a 4. Right, so I guess first here is we looked at the 3 and the 4, and then we're going to look at the 4 and the 2. And so I'm just going to, again, use just a single arrow, but what I mean by that is we're going to look at that element and the one to the right of it and see which one's bigger, and then swap those two if they're out of order. So here the 4 and the 2 were out of order because 4 should come after 2, so we'll swap them. And then we move along, we move the arrow to the next one, and we check if we look at the current one, which is a 4, then compared to the 4 and the 5, those are in order. So that is fine. And then we look at the 5 and the one to the right of it, and so we say, are 5 and 1 in order? And no, they're definitely not. So right here I'm going to swap the 5 and the 1. Oops. So the 1 comes first and the 5 comes last. And so what you should notice, if I rewrite this array to what it will be after we just finished here, is that the max is at the end, like with selection sort, but we've done a little bit more shifting around than if we did selection sort. So if we did selection sort, we would only swap one thing, but here we ended up swapping 2. And so why this is good is that, specifically, if we notice here, the 4 and the 2 kind of swap. So 2 is now in the correct place, and 4 is closer to where it actually belongs. 4 should be obviously the 4th element in this, and it started at position 2, but now it's a little bit closer to being in the right place. And so this is kind of the advantage of bubble sort, is that not only does it move the max up to its correct spot every single time, so now this is locked in, this 5 is definitely correct, but it also moves things closer to where they need to go. So the 2 is now exactly where it needs to be, and the 4 is closer to where it needs to be. And I suppose the 1 also moved closer to where it needs to be as well, right? Because it's at the end and it's going to kind of bubble down, right? It's going to phase through all of these. So let's do another iteration and take a look at this. One last thing I think I should mention is I stopped with the arrow on this 5 here, right? Because we're checking things with the element to the right of them, I don't want to go to the last element and check that one as well, because there's nothing to the right of it, so it wouldn't make a whole lot of sense. And you'll see that in the code when we get to it. that we're going to need to stop 1 early just because we're checking the thing to the right of it. Anyways, let's start over. So here we have an entirely new array, closer to being sorted, and I'm going to first look at 3 and see, is that sorted compared to the thing next to it? And if I check, is 3 and 2 in the correct order? It's not. 2 should come before 3, so I'm actually going to move it over. And so, you might say, okay, well, what you said earlier is now a bit of a problem because the 2 just moved out of the place of where it needs to be. And you would be right. Sometimes we are going to move things a little bit out of order when we do bubble sort, but generally things are going to kind of settle down and kind of form the way that they need to go. Right? So there we go. That does that. We've got 2 and 3 here. They're kind of in the correct order at least now, so that's good. Even though it's not in the correct position, it is in the correct order. And so that's kind of the key part. Anyways, we move along the arrows. We checked this one, the 3 and the 2. We said, okay, those are out of order. We'll swap them. And then I'm going to move here. We're going to check the 3 and the 4, and those are in order, so no swap is necessary. We check here with the 4 and the 1, and those are out of order. So I'm going to swap the 4 and the 1, so the 1 becomes here, and the 4 goes there. And then last, well, that would be the last one. Because we know 5 is in the correct position, I don't need to check the 1 and the 5 at all because it's going to be exactly there. And so you could walk all the way through the array and check everything that is sorted as well, but I'm going to attempt to optimize it when I write the code so that it doesn't check anything over there to the right. So if we, again, look at our array, what we have now, we have 2, and then 3, and then 1, and then the last 2, the 4, and the 5 are locked in. So similar to selection sort, how many ever times we've gone through the array is also going to correspond to how many things are for sure in the correct place. So 4 and 5 are for sure in their final place, so we don't need to try to sort them again. We know that they're right because this always moves the max to the end of the array. And so, right, we did 1 loop here, and we ended up with 1 thing that's sorted, and we did 2 loops here, and we've done 2 things that are sorted. Right, and the other thing to notice is one started at the end, and then it's kind of moving to the left, right? So it started at this last position, and then it moved left 1, and then it moved left 1. So 1 is kind of bubbling towards where it needs to go. It's bubbling down, right? It started at the end, and it's going to end up at the front, and that's kind of why we end up swapping things out of their final position, but we end up getting them in the correct order at least. Right, so let's do 1 or 2 more loops here. So if we start at 2 again, we'll look at 2 and 3. Those are in the correct orders. That's great. And then we look at 3 and 1, and those are out of order, so we swap those. And so the 1 goes here, and 3 goes here. And then that would be it again, right? So great thing about bubble sort is that it's going to check less and less every single time. And I suppose selection sort does that as well. But bubble sort will do this on top of that. Right, so there we go. Moved all those into the position. And then the last thing we need to check is, are the 2 and the 1 in the correct order? And so 1, 2, 3, 4, and 5. And so we would swap these, right? I'm getting a little bit ahead of myself, but we would check here the 2 and the 1, and we'd say, well, 1 and 2, those need to swap. And then we have a sorted array. Now there is an advantage to bubble sort, and I came up with an example here that doesn't demonstrate it, but let's just say I had an array here for an example that was shorter. It's going to be 1, 3, 2, 4. So what bubble sort exceeds at is arrays that are very close to being sorted. Bubble sort is not a particularly fast algorithm. It's a little bit better than selection sort. They're both of the same order, if we were to say this in like fancy math terms. But bubble sort has one advantage that kind of makes it useful, even though it is not the fastest algorithm or not particularly great in its runtime, and that's when things are very close to being sorted. So here, if we did a run through, right, we would start at 1, we check are 1 and 3 the same, in the correct order, and yes they are, and then we would check 3 and 2, are those in the correct order, and we'd say no, well 2 needs to come before 3, we would swap these, and then we would check 3, and 4, and see if those are the correct order, right? So as far as my array goes, on my second loop, I'm going to have it in 1, 2, 3, 4. So it is already sorted, right? Because this was pretty close to sorted. There was only one swap necessary. And as far as what we've gone over so far, as far as the computer knows, only 4 is sorted, because we can only be guaranteed that the max moved to the end, because we don't really have any knowledge of what the order is. But as human beings looking at it right now, we can say, well, that's sorted. And so the computer, or I guess what the algorithm does, is it will go through and try again. So it will say 1, 1 and 2, okay, those are in the correct order, and 2 and 3, those are in the correct order. And at this point, it actually does know it's done. And the reason it knows that is because if no swaps took place, then the list must be sorted. So if we consider what the swap does, the swap is only done when things are in the incorrect order. So if we don't do no swaps whatsoever, then it can't be out of order, which means that it's in the correct order. So the good thing about bubble sort is that if you run it and you get no swaps, then that's great. You can just stop right there. Bubble sort is able to be optimized in this way, and so even though it's not a great algorithm in terms of runtime, as far as you'll see if you take more computer science courses, it does have this advantage that it can be very, very quick if you know that the array is going to be pretty close to sorted in advance. So this is the one advantage of bubble sort. I guess the other advantage it has is that it's not very hard to write compared to other algorithms, so it does have that going for it as well. I would highly recommend using bubble sort for all of your programs over selection sort. I just wanted to give it as kind of an introduction. Anyways, now that we know how bubble sort works, let's go ahead and try to program it. Alright, we're back here. We're ready to write the code. I still have the same code with the selection sort and just the stuff that prints and sorts the array. And so we're going to need to do bubble sort. Similar to the way that selection sort worked, we're going to need to do 2 separate loops. So we're going to need to have an outer loop, and we're going to need to have an inner loop, and I'll explain them in a second. So I'm going to go I less than length, I plus plus. So this outer loop is going to represent, so go through all of the elements until they're sorted. I is going to represent how many elements have been sorted so far. Basically, this just represents how many loops we've gone through in terms of looking through the array and bubbling the maximum to the end. So that's what our outer loop, the I here, is going to represent, and then we're going to need to use a inner loop as well. And I said earlier that these are of the same order, which is just kind of like a fancy word that has to do with how long it takes for them to run. And one way you can kind of get an idea of that is the fact that they both use 2 for loops, right? So these both use 2 for loops, I and a j, and they both go through up to length to some extent. And so that's kind of where that comes from. And so you can kind of get a gut feeling for how fast an algorithm is based off of what its loops look like. Anyways, let us finish this a little bit. So we said we want to subtract I here because we don't need to go and resort the I elements that are already sorted, so I'm going to subtract those. And then I'm also subtracting by 1 here. And the reason I'm doing that was because of the way we said we were going to do it, where we're going to keep that arrow kind of and then just check things that are to the left and right of each other. And so if I go too far to the end, then I'm going to check the right of the last element, and that's just going to look past the edge of the array, right? Which is bad. We don't want to do that. So I'm going to subtract a 1 here to make sure we don't go past the end. Now I'm going to need to go through and basically just compare adjacent elements. So here I'm going to say if r sub j is greater than r sub j plus 1. And so what this says, right, is if the element to the left, the element j, is bigger than the element to its right, which is at position j plus 1, because plus 1 is always going to be 1 to the right of this, then they're out of order. Right, so this just says if the two adjacent elements are out of order, at least if we're doing things in non-descending order, that is least to greatest, then this is what we want to do. If we want to go from greatest to least, then it would be the other way around, right? I do recommend just using greater than and not greater than or equal to, just to save yourself some swaps and possibly make things faster. Then we need to swap. And so I'm going to go here, I'm going to create a temporary variable, and then we're just going to swap them in exactly the same way that we did earlier up here. So I'm going to set the temp equal to one of the two. I'll just make it the first one, I guess. RJ, I need to make sure I have an equal. And then I'm going to set RJ equal to the one that I need to swap it with, which is the one to the right. And then I will copy the one to the right into the part. So we'll say equals temp. And again, we don't need an else. No else needed, because while we only need to swap them if they're out of order, if they're in the correct order and we don't need to swap them, then we don't need to do anything, right? So we'd be good. And that should do it for bubble sort. This is the basic setup for it. Let's go ahead and run it and make sure it works. Okay, so I ran it, and we see that if we look at the bubble sort thing, it generates a random list here, pretty close to sorted actually, and then it puts them in the correct order. So it moves the -6 all the way to the left, and everything ends up exactly where it needs to be. So this works, and that's great. And so really it is just this easy for bubble sort. It maybe is a little bit harder to wrap your head around than selection sort, but the code is pretty simple, right? It's actually shorter than this, right? It's just, 3 lines of code and an if check. So it's really not too bad. But we said that there's an optimization we can do, so we should probably do that as well. And so I'm going to say is swap. And so I'm going to keep track of a variable for swapping. What we said earlier is that if we performed a swap, then we know that our array is not in the correct order, because if we had to swap, then things were misplaced. But if we don't have to swap, then that means that the list must be sorted, because if no swap takes place, then that means that the list must not be corrected. It didn't need to be corrected, so it is in the correct order. And what we will do here is we will say by default, no swap takes place. Right, so we will just say at the start of our loop, when we look through the array, we haven't done any swaps yet. If we encounter a swap, then we will mark it down. Here I'm going to just say is swap equals true. And so just consider, if we swap at any point, no matter how many times we swap in a single iteration, for a loop, not an iteration, I guess it is an iteration of the outer loop, a loop through the inner loop, then it's going to mark this true. And it doesn't matter if we mark it true a bunch of times from a bunch of different swaps. If it happens once, then we know this is going to set it to true, and by the end of the loop, we'll know that we did a swap. And so what I could do to optimize this is I can either say if there was no swap, then we just break, we're done. Alternatively, and what I would usually do is I would say and there is no swap, and then I would set this equal to false by default as well. That's how I would normally do it, just so that we can optimize this a little bit. So this is using uninitialized memory. I think it's because it's processing it. Yeah, there we go. Normally I would say don't write an if check and then break, because this part will get it for you anyways. But that's okay. We are going to maybe leave this here. I'm just going to comment it out and leave it. So I'll at least comment it so that we can see it. If no swap happened, the list is in order, and we're done. Right, and I could even maybe print J here just to see how many times it actually went through the list, and we would see that it probably, most of the time, doesn't go through the list all 10 times in this case, right, because we're doing 10 elements. We can optimize bubble sort a little bit this way, and that is what makes it helpful. Anyways, that was just a quick overview of two very common sorting algorithms. Definitely remember these, especially bubble sort. You will use them a lot. In the next video, we will take a look at a searching method that improves on the linear search that we went over previously, but that kind of hinges on the fact that the list is going to be sorted.